Let's take a look at quiz number 11. We are considering the solid that's under the plane z equals x, and above the rectangle, x goes from 0 to 1. Above 0 less than or equal to x less than or equal to 1 by 0, y goes from 0 to 2. Okay, so let's think about what this solid should look like. So we had to write a triple integral, a double integral, and now we want to write a single integral for this solid. Let's draw a picture of this solid because we have to go back to some Calc 2 techniques. What we're going to do is we're going to take the cross-sectional area and integrate the cross-sectional area over the height. So for the single integral, we're going to integrate the cross-section's area over the height. So for a double integral, we integrated the height over a region. And for the triple integral, we just integrated 1 over the solid. But for a single integral, we only get to integrate on one variable. So we have to we have to look at the cross-sectional area and multiply that by the height, which is going to be integrating that over the height. Let's draw a picture of what this looks like and see what our options are. So if we imagine, first of all, everything's going to be positive. So let's draw our x, z, and y axes. X is going from 0 to 1. Y is going from 0 to 2. And z, and we're looking at the graph of z equals x. So scroll. So if we think about the graph of z equals x, if we notice that this plane, z equals x, does not care about y. So whatever we draw in the zx plane, that just gets copied along for all values of y. So that's a big advantage that we have. Or so what we need to look at is the graph of z equals x. So the graph of z equals x is going to be in the xz plane. Let's look at what happens when y is equal to 0. So we're going to start down here at 0, 0, and we're going to go up at a 45-degree angle. So here's the line z equals x. So that's the line at 45-degree angles in the xz plane. We could drop this down to where x is equal to 1. So here x is equal to 1. And so this shows us what kind of picture we're going to get. Now this is going to be projected. So now we can start to see what all of our options are going to be in coming up with a single integral for this solid. because our solid is just just a prism. So the cross-sectional area is only going to vary in the z direction. Notice that in the y direction, it's always this triangle multiplied by 2. In the y direction, I can't remember what I just said, so I'm going to recap or start over, reboot the whole thing. In the y direction, the cross-sectional area is always this same triangle. And that makes sense because our equation z equals x doesn't seem to care about y. So one integral we could write is we could just integrate this area of the rectangle from 0 to 2, dy. So we could write this as a y integral. If we wanted to write this as an x integral, if we take a generic x value, we see that we'll have this rectangle where the width is going to be 2, and then the height will vary with x. So the height will be given by the z value and vary with x. That's if we integrate along x. If we integrate along z, we've got this big rectangle that's the floor, and then as we go up, we get smaller rectangles. It's always 2 for the y, but the distance, the height from this corner to this angled edge gets smaller as we go from the floor up to the ceiling. So those are the 3 possibilities. One of them, the dy, will have we're integrating a constant, and it's a triangle. If we integrate dx, we're integrating a rectangle that goes from small to large, ending up at this facing rectangle here when x is equal to 1. And if we integrate dz, we're integrating from the floor up. Any questions? So those are our 3 possibilities. So we can integrate the triangle dy. We can integrate the rectangle dz that goes from the floor and then starts up. Starting off at the floor. Or we can integrate some other rectangle dx where it ends at the large rectangular wall. Starts at this pointed part and ends at this wall. Integrating dz will be starting off at the floor, which would be this floor down here, and ends at the pointed at the top. So those are the 3 possibilities we have for the single integral. We can go, and that's one of the things that makes this problem tricky. We have a choice, but that means we have to make a choice. 2 of the choices are kind of the same, just in other directions. So we're integrating dz from the floor of this rectangle up to this line up here, this shrinking rectangle. Integrating x, we're integrating a growing rectangle. So both of those are going to have functions of z and functions of x. But the triangle integrating dy is just the same triangle the whole way through. So notice that's in the y direction. This triangle is always the same. We just take that area and multiply it by 2. And we can represent that with an integral since that was the request. I didn't actually care about what the volume of the solid was. We could just integrate, I set up an integral where we multiply this area by 2. Any questions? All right. So the triangle one would be a constant. The rectangle ones, the size of the rectangle changes, but the triangle is a constant. But the rectangles, those are variable. Any questions? Comments? Deep thoughts? All right, let's pause the video here and talk about other questions.